I'll begin by interpreting the problem statement. Pressure above the water is 10 kPa, which is about 1/10 of an atmosphere. Gauge means that the pressure is measured relative to local ambient pressure. The tank is enclosed except for this nozzle. The distance from the free surface to the nozzle is 0.5 meters. The water temperature is 20 degrees C. The goal on this problem is the velocity of the water jet. So velocity of the water jet right here. This statement means that the speed of the water surface, which is this speed, v sub s, is much less than the speed of the water jet, this speed. So we can write that v sub s is much less than vj. Next, I'll connect this problem with what I already know. A tank of water, of course, will drain due to gravity, and the extra pressure on top will simply make the tank drain faster. When I see a draining tank with flow out a smooth and tapered nozzle, I recognize that this problem is a classic application of the Bernoulli equation. Here is how I define the situation in my documentation. I sketch a situation diagram. I document my assumptions. These two assumptions are required in order to justify use of the Bernoulli equation, and this assumption was given in the problem statement. In my goal, notice how I use the label speed because I know the direction of the velocity vector. To reach my goal, I selected the Bernoulli equation. Thus, I'll next go back and modify my situation diagram. I sketched my streamline, shown by this dotted line here. I labeled points 1 and point 2, and I labeled the datum at the elevation of point 2. Now I've written down the Bernoulli equation and made a sketch so you can see what's going on. Let's do term-by-term analysis. The pressure at 1 is known, that's 10 kPa gauge, so that's 10 kPa gauge. This is a specific weight of water. The elevation at location 1 is also known. The elevation at location 1 is 0.5 meters. The velocity at 1 is approximately 0. The pressure at 2, because the jet is discharging out to ambient, is 0 gauge. So 0 gauge. The elevation at 2 is 0, because that's my datum, and the velocity at 2 is my goal. Let me clean up this equation. Here is a reduced equation, and I can see that I have one equation and one unknown. So next I look up the value of specific weight of water, document this, and then I go to calculations and solve for my goal, which is the velocity at the exit plane of the nozzle. All I need to do now is plug in numbers. So I solved for the velocity at 2 from the Bernoulli equation. That's this equation. I substituted in numbers, and the final answer is that V2 is 5.46 meters per second. Review comment number 1. Whenever I see converging streamlines, such as in a smooth nozzle, shown here, I think, aha, this is a likely application of the Bernoulli equation. Review comment number 2. It's very useful to use a systematic process for the Bernoulli equation. Step 1 is identify when the Bernoulli equation fits a physical situation. Step 2 is I sketch the streamline. I label points 1 and 2. Step 3 is I write the general form of the Bernoulli equation in head form or pressure form. And step 4 is do a term-by-term analysis. And I illustrated this systematic process for you in this example. Review comment number 3. Whenever you see a free jet discharging from a reservoir like this, you can set the pressure on the exit plane, that's this plane, equal to ambient pressure. And if the ambient pressure is 1 atmosphere, the pressure on the exit plane becomes 0 gauge. And we'll use this fact over and over in fluid mechanics. I hope you found this example useful. I'll see you next time.